Hello, and welcome to our presentation for the distributed search engine with hash-based partitioning. And I'll be demonstrating on a search engine system that implements a search engine with distributed indexing using hash-based partitioning. So our system, it demonstrates 10 different data structures working together to be able to solve a real world problem, like how to efficiently search through millions of documents using a distributed architecture. So basically, our system runs in two different ways. We have the CLI and we have the graphical user interface. Like that. But today we'll be focusing on using the CLI. Let's go back to our command prompt, and then it lists all the commands. So our problem statement, it was focusing on building a scalable search engine, and most of the challenges that we were able to address is the first, document indexing. Like, we needed to be able to add the documents up to the system quickly, and this is where the hash implementation insertion was working. And then we also added like when a user searches, they need to be able to find the result in milliseconds. Uh, and then we also added the constant term lookup, that where one can find all the document containing a term in constant time. And also we also added a stack-based history system, which will allow the users to be able to go back and forward through previous searches. So basically, our system architecture, it included the client interface, which is the command line interface, as shown over here, and also our graphical user interface, as previously shown. We also have the query queue, where when a user is able to submit a query, it is first placed in a queue. Then we also have the search aggregator. This is mostly like the brain of a particular system. We also have the shards 0, 1, and 3. We have this, and we also have the supporting architecture. Next, now let me demonstrate the CLI interface and show you each of the commands and how each data structure is demonstrated. So when I run the main.py, the system automatically loads all the 8 demo datas, and then it shows all the available commands. And let's start by now keying the commands. Let's start by the statistics. The stats command, it shows us the current state of the system. Right now we have the 8 documents, 55 unique items, terms, and 3 shards. And we don't have any pending queries, and the history is also empty. This is able to give us the baseline to compare against after we perform the operation. Now, let's see the shards. This shows us the terms are distributed across our shards, and each shard has a roughly of 8 to 18 to 20 terms, and it has a balance score of 0.67, which is indicating that our distribution is very much balanced. Let's start the command by adding a document using the add command. So so the document is given a very unique ID, let's say unique ID number 9, and then the system automatically updates the important index, and then it then redistributes the shards. This one was demonstrating the hash table insert option. Now let's check our statistics. After I added the document, the document count increased from 8 to 9, and then the unique terms they increased from 55 to 56, and the system then updates all the data structures to be able to reflect this change. Next, we have the search command, which uh, okay. So for the search command, it performs a distributed search across all shards, and then the query is passed and set to all shards, and then the results are then matched using the min heap. Next, we're gonna do the queue as search. Let's put it as high. So when the so what I've basically done is that I've queued the machine learning as a high priority query, and then the query is stored in the high priority queue and will then be processed before the other queries because they are in line of train. There's the high, the normal, and the low. Let's queue more queries. So we have queued two more queries, the data structures as normal, and then the algorithms as normal. When we queue the multiple queries with different priorities, the system maintains three separate queues: high, normal, and low. And here, it demonstrates our priority queue implementation. Next, we have the process command, which dequeues and processes the next query in the queue. Uh, Over here, it demonstrates the QDQ operation, where the high priority query is processed first, and then the results are returned before the others are processed. So, uh, so when processing all the queued queries, it shows the first in first out nature of the queues. The queues are processed in the priority order: high first, then normal, then low. Next, we have the back, which demonstrate our stack data structures. It pops the previous query from the back stack and then makes it like it is the one that is there, the current query. It's like how you press the back button when navigating Chrome. Next, we have forward command, which pushes the current query onto the forward stack, and then it pops the next query. Next, I'm gonna do is a test, which this command, it runs the 15 comprehensive test cases, which validates all the data structures and operation to be able to ensure that and confirm that the system is working correctly. Next, we have the benchmark, which shows our transaction levels. Like it runs the performance test on all the data structures that we can see, like the hash map, the inverted index, and also the heap top, the heap and all that. And that brings me to the end of my system.